Let us try to understand the induction motor, its operating principle, and use the model of the induction motor in simulation. So you see, this is a representative segment of the rotor. You have the rotor conductors here shorted on either side to form the squirrel cage. The rotor current flows through the rotor conductors, this is IR, and due to the currents flowing in the stator, there is a axial flux B that is developed, and this axial flux B and the rotor currents interact to produce the Lorentz force, and this Lorentz force is the one which makes the rotor conductors, rotor bars to rotate, and hence the shaft of the induction motor. So this is the torque production principle. So this figure here shows a representative schematic of the induction machine. This is a cross section of the induction machine where the inner circle is the rotor. It's a cylindrical rotor, and the outer orange colored laminations are the stator. The stator that is shown here appears to be salient pole type, but in actual practice is not salient pole type. However, this picturization gives a better visualization in understanding the operation of the induction motor. But in reality, the stator will not have saliency as shown here. So you have three sets of coils: the A coil here, the B coil, and the C coil, and they are spatially distributed 120 degrees apart. They can be represented in the form of axes, three axes. You have the stator A axis, stator B axis, stator C axis, and any parameter along the A coil like the current, voltages can be represented along the A axis. Parameters of the B coil like the currents, voltages, and the flux linkages can be represented along the B axis, and likewise the C coil parameters along the C axis. So this will give rise to spatial vectors, and you can have at a given point a resultant spatial vector called the space vector. Typically, if XA represents a parameter along the A axis, XB represents a parameter along the B axis, and XC along the C axis, you can represent the spatial space vector X as XA plus XB e to the power of j 2 pi by 3. This corresponds to the 120 degree spatial shift. Xc e to the power of j 4 pi by 3, where 4 pi by 3 corresponds to 240 degree spatial shift. So this is a typical block diagram of an induction motor electric drive, where you have the prime mover, the induction motor here, and there will be an inverter consisting of IGBTs and an electric power source, which could be the mains or batteries. So there will be bidirection for power flow. You will have energy flow in this direction for motoring, the green one; the red direction, the reverse power flow during braking, regeneration, regenerative braking, those kind of situations. So you will be sensing the motor terminal parameters like the terminal current, the stator currents, and the stator voltages. The sensor here, either the hardware physical sensors sense the currents and the voltages, or you will be having estimators to do the job, and there will be a control units. It will take a set of performance drive commands, pass it through a modulator, a PWM modulator, space vector PWM modulation, which will modulate, switch on and off the power semiconductor inverter, so that you get the required performance out of the induction motor prime mover load combination. There are several strategies for speed control of the induction motor. One is called the stator voltage control, which is the simplest. It's a very simple circuitry. You just change the stator voltage. As you vary the stator voltage, there will be speed change. However, this is very poor in efficiency and has very low speed range. The other more popular method, the V by F control or the scalar control, achieves a much wider speed control range. It has a higher starting torque, and the low speeds you need to give a voltage boost because the stator resistance dominates at low speeds. The third and much more accurate method of speed control is called the field oriented control or the vector control. Here, the dynamic structure of the induction motor is transformed in such a way that it appears similar to a separately excited DC motor. Thereby, you have decoupled control of flux and torque, and thereby has very good dynamic response. Dynamic performance is the best among all the different methods of speed control of the induction motor. From first principles, one can easily derive the model of the induction machine. So this is the consolidated summary of the model of the induction machine. This is the dynamic model of the induction machine. You see it in state space representation. The state vectors, the state variables that has been used here, IS alpha, IS beta, or the stator alpha phase current, stator beta phase current in the alpha beta 2 axis frame. IR alpha, IR beta are the rotor alpha axis, rotor beta axis currents in the alpha beta frame. So this side you have the differentials of IS alpha, IS beta, IR alpha, IR beta. So X dot is equal to AX plus BU. The inputs are the voltages Vs alpha phase stator voltage, alpha beta phase stator voltage in the alpha beta frame. LSS is the stator self-inductance, M is the mutual inductance, LRR is the rotor self-inductance, omega M is the shaft speed, and RS is the stator resistance, RR is the rotor resistance. Now with these, the dynamic model of the induction machine is fourth order model as given here. The torque is given by this 2 by 3 M is the mutual inductance, IR alpha at IS beta minus IR beta into IS alpha, and the torque dynamic equation TD developed torque, this is the developed torque, minus TL the load torque should supply J d omega M by dt, any acceleration plus the friction loss B omega M. So this becomes the entire model of the induction machine. If you implement this, then you would have your induction machine model. So let us see how we implement this. This being a direct equation, we can use the octave simulation environment for directly entering this motor model and trying to understand the induction machine. We can also put this model in sub-circuit and also make a symbol for induction motor and also use it in SPICE. We will do both examples and see.